get it going. So first thing first is I tried to record this lecture, spent 1 hour and a half on it, and at the end, the software just crashed on me. I didn't get recorded, of course. I forgot to click the save button, so my bad. And frustrated, of course, right? But at least I prepared myself well in this lecture, so I know exactly what I'm going to teach today. Okay. All right, so I practiced, so it should be good. Well, some of you are asking for the quiz and exam, but unfortunately, I don't have that yet. So, in other words, for the quiz and exam, we're not going to have anything until I come back. So, the TA is grading the quiz and exam, I believe, right? And then I am going to have all this information ready. Then you guys will have it next Tuesday, not today, okay? Next Tuesday. Alrighty, so let's say look at what we're going to learn today. So basically what we have been learning is displacement of the beam. So imagine you have a beam and then N is fixed, then you have force applied, or maybe chances are you have a different sections, right? Different cross-section areas. So what is total displacement on that? And maybe you have another force F1 on top and the bottom, right? So therefore your total displacement is nothing but summation of FL divided by AE, because in each section there's different cross-section areas, right? A1 and A2, and maybe the force is different too. So all you need to do is a simple summation, okay? All right, now in the beginning we also learned there's lots of a force that might be uniformly distributed or maybe non-uniformly distributed across the whole length, right? So therefore, in this case, every single section has different cross-section areas like A1 and A2 and A3, right? So all you need to do for that case, displacement is equal to Fx divided by Ax, 1 over E, and dl, and 0 to L, right? So in other words, when you have a non-uniform length across the whole non-uniform cross-section across the whole length, you'll have to do the integration to find the total displacement. Okay, so today probably we're going to see one example or two that's related to that. Okay, so let's get started. Let me give you one example that has those non-uniformly distributed force. Okay, all right. So here's an example. We have a post, just like a beam or anything. Okay, it's made of wood, and it's a special type of wood. Of course, I'll give you the material property later. And it has a diameter of 60 millimeters. Okay, 60 millimeter diameter. Now, if it is subjected to the load of 20 kilonewtons, 20 kilonewtons of force, not that high, right? Considering the 60 millimeter of diameter. And the soil provides a friction resistance that is uniformly distributed along its sides of W equal to 4 kilonewton per meter. I'll tell you what does that mean later, all right? Okay, and determine the force F at its bottom needed for equilibrium. Okay, so also, what is the displacement of the top post at point A? So basically point A is the top of the post with respect to bottom point B. Okay? Alright, and then Young's modulus of the material is 13.1 times 10 to the 9 Pascal. In other words, it's like 13.1 gigapascal. Okay? Alright, so that is the problem. Okay, so let me draw that figure for you. So it's a wood post, and then it's buried in soil. So let me use the soil color right here. So it's buried in soil, as you can see. Now, in the bottom, let's just say there's a piece of concrete. Let's just use red for the concrete, shall we? Okay, all right. And here's the geometry information. First of all, there's a 20 kilonewtons applied on the top. This is point A, as you can imagine. And because A is the top point, and the B is the end. Okay, B is this point. Now, also the fraction of the soil is linearly distributed. In other words, it's along the whole sides of this post. Okay, and the total force concentration is described by 4 kilonewtons per meter. Now, total length of the shaft from top to bottom is 2 meters, or total length of the post, in other words, all right, 2 meters long. So just like a distributed load, you have distributed load density multiplied by the height is supposed to be the force, right? Okay, so there's one more force here at the bottom on the concrete. So let's say this is force F. Okay, now it's asking for two things. First one is what is the force F at its bottom needed for equilibrium? Second, so what is the displacement of the top post? Okay, so A respect to B. So in other words, it's asking two things. One, what is this force F, right? Second, what is displacement A relative speaking to C? Okay, all right, so let's look for that. Now, of course, first thing first, free body diagram. No matter what we do, free body diagram is the most important. So let's look at it here. You have a force going downwards, 20 kilonewtons, a force going up, F, and the supporting force goes upwards. That's caused by the soil. We call that also supporting force, right? They say a soil give you W 4 kilonewtons per meter, and total length of the post is 2 meters long. Okay, so therefore I can have a equivalent force that's caused by the soil, just like distributed load, right? So therefore we can simplify this free body diagram into something like this. Show you right here. Okay, so 20 kilonewtons F, and then over here it's equivalent to a force right in the middle, equivalent by the way, okay? Pushing up, then that force is equal to 4 times 2, that is 8 kilonewtons. Okay, so density times height. All right. Okay, so using your knowledge, summation Fy is 0, or the force in the y direction is 0, of course y, O, x, right? So I know the force going down is 20 kilonewtons, and the force going up is F plus sorry, not f. Take that back. Equals to a going down 20, 8 plus f. 8 is a force caused by the soil, right? And then another f over here is caused by the reaction force from the concrete at a point B. Okay, point A, point B. So therefore, I automatically know F is equal to 12 newtons because 12 kilonewtons, because 20 minus 8, that is my reaction force. Okay, so we'll automatically know the reaction force. Okay, now the second thing is we need to find out displacement. Displacement AC, in this case, I say we will have to use this integration. Why is that? Because F is a distributed load at each section. It's different, right? It's not uniform, okay? So, sorry, it's not a concentrated load. So therefore, it's not a constant. So therefore, we have to use this integration right here, okay? So let's see how we can do it. Now, we still need to do a free body diagram. So this is our free body diagram of AB we just did. So force going there's a force going downwards, and then there's force going upwards all the way, right? Seems like that. And then there's supporting force, right? So I have to do integration from all the way from 0 to 2, right? So let me see, what if we just cut it right here? See what is the free body diagram look like? Just choose arbitrary location, okay? So here's my force going downwards of 20 kilonewtons, and here's my equivalent force. Let's say from here to the arbitrary location, it's distance y. Okay, so here I have equivalent force pushing upwards. That's equal to 4 times y. Makes sense, right? Because y varies from 0 to 2. Okay, all right, and then also, of course, let's assume this internal force, because it's internal force, all right? So of course one of them is going down, the other one is going up. Let's assume it's going downwards, Fy. Okay, so just be consistent, and so let's see how we can calculate that. First of all, we know, using our knowledge of a Fy going downwards and 20 going downwards, that should equal to 4 times y, right? So Fy equals to 4y minus 20. Now, some of you say, okay, how do you know the Fy is going downwards? What if it's going upwards? That's fine, no problem, okay? You can assume the Fy going upwards. Later on, you just find out actually the sign might be negative. That means your assumption is wrong. It's just like free body diagram. When you take up the reaction, you can assume the direction of the force, okay? So it doesn't matter, okay? The direction of Fy here, it doesn't matter. So this is with a unit of kilonewtons, okay? Now, in order to find out what is the displacement, we need to use this equation, like I mentioned, AC delta AC, that is equal to 0 to L and Fy divided by AY and 1 over E and then dy. Okay, all right. Because E is Young's modulus, it's a given, right? 13.1 gigapascal. And then the things change is Fy and Ay. Okay, now I also know Ay, I think it's a constant, right? Because it's a cylinder with a diameter of 60 millimeters. It's constant across the whole length. So therefore, A is also constant. But really, the only parameter that change with Y is Fy. Okay? This is the only tricky part. So therefore, let's move the A and E outside of the integration, because Ay is a constant equal to A equal to pi over 4 d squared, and the d is 60 millimeters. Okay. All right. So Ay is moved outside of the integration, and 0 to L, and Fy is 4y minus 20, and dy. Okay. So that is my integration of these displacement from A to C. Okay, so let me make sure this thing doesn't get in your way. Then we have AE right here. Now, integration of 4y is nothing but y squared divided by 2, because y integration is y squared divided by 2, right? Now, integration of 20 is 20 times y, okay? And then it goes L, the maximum length, which is 2. So therefore, in other words, the upper limit is 2, lower limit is 0, right? So you plug in y equal to 2 minus plug in y equal to 0, which is 0, right? So it doesn't get any complicated than that. Okay, so we can plug in when y equals to 2, that's 2 squared divided by 2 minus 20 times 2, okay, minus everything is 0, so 0 minus 0, so 0, okay? So we don't have to worry about that. Then the next thing is calculate the things out. So AE still that, and internally this is 16.8. 16 divided by 2 minus 40, right? Okay, so therefore it's minus 32. Now, be careful. Divide by AE, okay? Don't forget that. All right, so 40 minus 20, look at here. It has a unit of what? Kilonewtons, okay? So when you do this displacement, I want to make sure, remember FL divided by AE, I want to use newtons, I want to use meters, I want to use meter square, I want to use Newton per meter squared, in other words, Pascal, right? So I use a standard units, so it comes out, the displacement can be in meters. So make sure you don't forget this. Why? Because it's kilonewtons, right? I want to transfer that to newtons, so don't forget a 10 to the 3, okay? That's very important, otherwise it's going to throw your answer off by 3 orders of magnitude, okay? All right, the next thing is plug in the cross-sectional area and the Young's modulus. Cross-sectional area is nothing but pi over 4 d square, right? D is 60 millimeters, in other words, 0.06 meters, okay? So now this is meter square, okay? And Young's modulus, 13.1 gigapascal. Giga is 10 to the 9, okay? So therefore, Pascal, meter square, Newton. All right, perfect. So use your calculator, right? Find out the displacement, 0.8639 times 10 to the minus 3 meter. That's the answer. Or in other words, it's a 8639 millimeters. Okay, you see it's a very, very small displacement. Now, the negative sign tells you it is compression, which makes sense, right? You have a post and it's supported in the bottom, in other words, and you are applying force on it, right? Although the soil gives you certain supporting force, but you still have to have supporting force at the end. So chances are this whole post AB is undergoing compression. So of course, you see this negative displacement here, right? Negative means compression, okay? Make sense? Alrighty. So that is that. It's very, relatively speaking, straightforward, and that's how we do it, okay? Now, just want to be clear. So when you have a distributed load like this, okay, then it's going to give you integration for displacement calculation. Now, if you have something like what we did before, we have these ones, F1 or F2. Okay, so that way you only needed to do a summation of FL divided by AE, right? Because everything is linear, so there's no distributed load at all. So we can just plug in the F. Okay, make sense? So this is way easier. But as you can see, you just do one integration. All you did is this, right? So this is the key part. Nothing too fancy. Okay. All right. So I'll let you copy the answers if you have not yet, and then we can move forward. Okay. Now, the next thing is I want to introduce some other topics, which I can have 2 more examples followed by that. The other topic actually is very similar to the things we did so far. all right? But it's with a little different boundary conditions, and I want you guys to have the knowledge of how to solve for that, okay? Alrighty, and oh, by the way, I am going to post these, which as you already see, I'll post these lecture video on YouTube. All right, so therefore, if you don't understand any part of this lecture, you can go back and watch the video over and over again, however many times you want. Okay, so don't worry about it. So we can just we can play it again in the future if you want. I mean, you can do that. Okay. Alrighty, so next topic I want to mention is a statically indeterminate axial loaded member. Alright, it's a very weird name. I don't know why they came up with this name. So why they have to use this complicated word, what's like indeterminate, right? So but once I draw that for you, you will know exactly what it is. What does that mean? Okay. Now, chances are most of the time you will have a member that's encasted into a fixed boundary conditions. For example, look at this building here, right? You have these I-beams that supports whole structure, right? So the I-beam is, of course, it's connected to the ceiling, right? For example, this is our ceiling, and the bottom is connected to the floor. Okay, now some of the beams are like that. If you look at how they build the building, right? Especially those wood frames. Okay, so imagine this member is connected to the ceiling and then it's connected to the floor. So both ends, I'll show you, both ends on top and the bottom, it's fixed. Okay, so let's imagine this is our point A on the top ceiling. This is point B in the floor. Now, if I have a force right in the middle applied with a magnitude of P, then chances are the displacement of AB is 0, right? Because it's fixed. It's attached to the ceiling and attached to the floor. So no matter how much force you apply along the AB, you are not going to see displacement. So in other words, AB is always equal to 0, right? Okay, now in that case, this is a very interesting problem. Let's assume this is C. Okay, now let me ask you, displacement AC, let's do it this way. Displacement AB is nothing but displacement AC plus displacement BC, right? Because the beam AB equal to AC plus CB. Okay, so very simple. Now, is AC equal to 0? Or is BC equal to 0? I think none of them are 0, right? Right here, this is a non-zero term and this is non-zero term. Okay, now, might be hard to see for you guys, but let's do this. Imagine a fixed top and bottom, two springs. Let's say this is K1, this is K2. I have a force, right, applying in the middle, force F. Okay, what is spring K1 undergoing? It's undergoing tension, right? Or let's call that extension, shall we? Extension. How about K2? It's under compression, right? Okay, K2 is under compression. So therefore, as you can see, if I have a force applied on the spring system, one of the spring on top is going to see extension. It's going to become longer. But the spring in the bottom is going to become smaller, right? Simple. So same thing here. Now, this beam AC, let's use a orange color per se, AC. And this beam in the bottom, BC. They are just like two springs, right? Remember, I told you guys the Young's modulus and the spring constant are very similar, right? Young's modulus, spring constant, right? Force displacement, right? Because this is nothing but force divided by a constant. This is nothing but displacement divided by a constant, right? So spring constant and Young's modulus, they are very similar physical quantities. It measures how hard it is to deform certain materials, right? Okay, so therefore, I say, let's come back here. Not only AC is not zero, I know AC is a positive number, bigger than zero, extension. BC is smaller than zero, right? So a positive number plus a negative number equal to delta AB, which is always zero. Make sense now? Okay, so positive, negative, zero. Okay, important things. Let me write it again here. AC plus BC. And this is zero. So that tells you if I only look at absolute value of the displacement, these two quantities has to be the same, but one of them has to be positive, the other one has to be negative. In this case, AC is positive, BC is negative, right? It's just like plus 5 and minus 5 together is 0. Make sense? So tells you AC and BC, they have to be the same absolute value point of view. Okay, so that can help us solve a lot of problems. Okay, so now let's go back to the concept I just introduced. The concept I introduced is called statically indeterminate axial loaded members. So that means, in word, when the force equilibrium condition alone cannot determine the solution, the structural member is called statically indeterminate. Okay, for example, just like the example I just showed you, there's a force applied in the center, right? Now, ask you what is the free body diagram. So you would tell me the free body diagram looks like maybe here's FA, and then here's FB, B. Then here is my force P, right? SC. So the free body diagram becomes, summation F is 0, right? And then FA plus FB are the force going upwards. That equals to the force going downwards P. Force going upwards equal to force going downwards. Okay, and again, I don't like to use positive and negative. Okay, going up equal to going down. All right, so only use the force relationship. P is a given value. FA and FB, they're both unknown. So two unknowns, one equation, we can now solve for it, right? How do we do that? We know this, right? AB is 0. Chances are delta AB is 0. We use our knowledge of FL divided by AE, right? You can calculate the displacement. Chances are that's going to give you another equation. So couple these two, you should be able to solve for it. Okay, make sense? All right. So in other words, the only thing new is we introduced this, where you have fixed conditions on both ends of the beam. Then you have total displacement is always 0. Okay, that gives you another equation that can help you to solve for these unknown internal forces. Okay, such as FA and FB reaction forces. By the way, okay, so I guess let me just stop here very quickly because I recorded it for a